Okay, so the next speaker is Fiona Porter on anomaly detection using local measure of uncertainty and latent representations. So that's, yeah.
Right, cool. I think I'm coming through all right. So hello, everyone. And thanks for all sticking around till near the end of this conference. Thanks to the organizers for organizing it. Yeah, today I'm going to be talking to you a bit about anomaly detection using uncertainty in latent space. So, to begin with, as you've heard from several talks already, there are a number of next-generation instruments which are either just coming online or will in the near future, which are going to drastically increase the number of sources that we can detect. But this comes with the logical problem that we are going to have so much data to look through that we just physically cannot have people look through it to identify them all. There aren't enough master's students in the world. So, with that in mind, machine learning is, of course, the obvious solution for rapid and rough and human accurate class labels. However, a thing we need to keep in mind is that because some of these surveys are going to open new regimes of observation, potentially there might be sources which we have never seen before, whether that's because they are at a high enough redshift that they represent some morphology which is very early in evolution, or they might be genuinely just something we haven't even theorized to exist yet. So that's profoundly exciting, obviously, and we want to make sure we don't miss any of those. It is pretty hard to just train a standard classification model to identify something when we have no idea what it's going to look like. And while in the past we've had some excellent serendipitous discoveries, which have opened new fields by themselves, case in point, pulsar astronomy, we can't rely on those serendipitous discoveries. What we need is going to be robust and reliable anomaly detection. Now, a number of methods for doing this do already exist. I'll point to Astronomaly by Lochner and Bassett for a really interesting one. And of course, we've already heard about self-organizing maps today. But these are largely unsupervised methods. They don't provide the classes that we would need for, our labels. And as well as this, it means they form an additional part of the pipeline. So what I was curious to know is there a way to do anomaly detection as a byproduct of classification? So a quick rundown of the model and data. What I'm using for this was just a simple variant on Linnet 5, a very standard CNN architecture. The key thing to pay attention to here is Monte Carlo dropout, which essentially just allows the model to produce a number of different responses each time you pass an image to the classifier. It doesn't give you the constant response that your standard CNN would. The images that I'm using are all FR galaxies from the Mirabas dataset, which I made. If you're not super familiar with radio astronomy, you don't need to know too much, but essentially it's a binary classification scheme for FR1s, which are core brightened, and FR2s, which are edge brightened, or at least that's what was originally posited. But since then, all sorts of interesting morphological subclasses have come up, including hybrid galaxies, which look like one half FR1, one half FR2. So for this work, I trained a binary classifier on the binary FR sources, and then used a total of 108 hybrid sources as anomalies, as things which look close enough to genuine binary FR galaxies that they might conceivably be mixed in with the population. Oh, and the dataset is publicly available if anyone wants to have a play with it. So let's look at some uncertainty measures. A fairly logical one to start with is one which has been used in the literature by a number of people. Entropy, which is an information theory metric, which gives you a measure of the total amount of uncertainty in the model for a prediction. It does require that your model is capable of giving variable outputs for the same image, so that's why we need the Monte Carlo dropout. It's minimized when your model is always predicting one class with 100% accuracy every single time you run it, and it's maximized when it's equally probable for all classes every time. So, I had a look, and the immediate response was that entropy by itself is not terribly useful. So, we'll see if I can get this working. What we have up top, these are the standard FR galaxies, whether they are correctly and incorrectly labeled. And the first thing we see is, well, okay, the incorrectly labeled sources have high entropy. That's good. It doesn't know whether they've gotten the right label, which is good because it hasn't. And the hybrid sources are also at high entropy. Again, good, we've got some uncertainty there. But the distributions do completely overlap. If you're only looking in this highest entropy bin right here, about a quarter of the sources are genuine hybrids. About 30% are mislabeled FR galaxies, ones which have been labeled FR1 when they are FR2 or vice versa. And all the rest are, in fact, correctly labeled galaxies. And at the moment, you know, that's not sounding too bad. But at this point, we've got a data set where about 10% of the sources are in some way anomalous. Drop that down smaller, and this rapidly ends up with you looking through a bunch of sources which are correctly labeled or completely standard. So it's not very good for outlier detection in itself. So what about latent space, since that's been quite a topic of discussion? So these latent representations are taken from the final layer of the model just immediately before the normalization to give you your predicted probabilities. So there is some nice logical ordering in the latent space where this cluster up here, as you go up this way, you get increasingly more probable to be FR2s. This way, increasingly probable to be FR1s. And in the middle, you've got this zone of confusion, which is where most of the misclassified sources live. So that's great, that looks promising. Do hybrids live somewhere different from standard FRs? And unfortunately, the answer is no. They do have a bit more of a spread in latent space, and they do overlap decently well with this sort of confusion zone, but you also get some quite high predicted probabilities for ones all the way out here. The model also doesn't consistently think hybrids are FR1s or FR2s. It thinks they could be either, which morphologically makes sense. But still, that's a no-go. So the next question I asked myself is, well, what about both of them? Is there some way of combining these metrics? So entropy in this latent space generally increases towards the center and then decreases out towards the edges. It's not strictly linear, in part because we've got all that dropout in there. So are the hybrids higher entropy than FRs for their region in latent space? And this is something which I termed local entropy, which I calculated by finding the 10 nearest correctly labeled, critically, FR galaxies from the training set. So that's what the model knows should be there. And we declare a source anomalous if it's more than 3 sigma from that local entropy. So does this one work? At a glance, it's actually pretty useful. So you'll see in the middle, we still have a number of hybrid galaxies which are going missing, but they are in that maximum confusion zone where we might want to look already. The ones that we're catching are the ones which are out here quite mixed in with the standard FR galaxies. We catch 31 of 108 of the hybrids, and every source over 3 sigma is a hybrid. We do not flag a single actual FR galaxy using this method. Now, this was the point that I wrote the abstract for this conference. And I was very excited by this. This looked very promising. So I decided, okay, well, the next thing I'm going to do is just make sure I do this nice and thoroughly. I'm going to look over everything, make sure there aren't any weird circumstances where it happens and others where it doesn't. And unfortunately, it doesn't always work. So I did decide to try a bunch of different things with this, including playing around with the training parameters for my model, tried some k-fold cross-validation, and even when you are using the exact same model architecture and the exact same data sets, sometimes it just fails to work. So you see here, we do have a small number of galaxies being flagged. I believe there's 6 in this one, as opposed to the 31 we had before. So 6 out of 108, not the best. And I'm still trying to figure out exactly when this works in hopes I can get something a bit more reliable from it. But with that said, even if it only flags a couple of anomalies, all the sources over 3 sigma from the local entropy are still hybrids, and we are still not flagging a single actually in-distribution galaxy. Which, for something which requires no additional model training, no additional algorithms, just uses the result. You just need to stick some extra dropout onto your model, and this appears to pick out at least some. So it's not perfect. It's something which I definitely need to do a bit more work on before I get a paper written up on it, but it has some potential, I like to think. So anomaly detection is going to be very important to the field, especially as we're going into increasingly towards big data astronomy. And combining these uncertainty measures, which we do just sort of get for free with our classification models, means that we don't necessarily need quite as much work in our pipelines for separate anomaly detection. There are a couple of different things I am looking to do to make this a bit more reliable, including making sure my uncertainty calibration is properly set up, trying out some different uncertainty measures, and also trying to find something which will improve local entropy in sparse regions, because that's, of course, the weakness of taking an average. If there's not many data points out there, it's going to get a little bit less reliable. In the meanwhile, though, if you are interested in playing with the data set, there's a QR code right there. It's the paper on archive. There's all my contact stuff, and I'll be happy to take any questions.
Thank you. We have some time for questions. First in Paris, Nabila.
Thanks for the talk. I was wondering what type of calibration effect you're fearing the most from the point of view of the analysis.
As in, what do I think might be the problem with it as is?
Yeah,
or?
exactly.
One thing I'm a little curious about is whether there's an issue with the uncertainty measures being either under or overconfident. Because what I've found is the one which I used even in this work is, technically speaking, quite underconfident. I'm assessing this with something called expected calibration error, where we say if something is in the 10th percentile of uncertainty, we expect about 10% of sources to be misclassified, and so on and so on. So that's something which I do need to look into in a bit more depth, just to see if that is a factor.
Thanks. Yeah. Okay, Gregor.
Thanks. I'd like to know, so the uncertainty you measure through MC dropout.
Yes.
So for after every path in the network, the output of your network is the best class or the probability of each class?
The actual probability. So that's going to, usually what you see is that unless it's very close to the 50-50 mark, it's generally going to stick to the same class every time. It's just exactly what normalized probability outputs is going to be different. And similarly, exactly where it lies in latent space is going to be different. When it came to plotting the latent space representations, what I went for was the version without dropout to give me a nice, consistent map.
Okay, thank you.
Maybe we have a question in New York.
Yes, we have Ashley.
Hi, great talk. So I apologize, I can't quite remember the name of this variable, but you contextualized the talk in the beginning by telling us if I make a cut on something I think was called Z, and it was greater than 0.6, I have a purity of anomalies with 50%.
Sorry, I'm not quite...
You showed two histograms on a plot.
Oh, these ones, yes. So this is
sure.
this is
my main point, actually. Yeah, I think my main question is a concern that, well, you're showing us now that you're increasing purity in the true anomalies of your sample, but I don't know how the completeness of your sample has been decreasing. So if I just kept making that simple cut, but more stringently, could I not also just have a small sample of pure anomalies? Why do you need to do this entropy step?
Unfortunately, there's a pretty significant overlap. There does not seem to be, even if you put this into additional number of bins, you're going to really struggle to find any sources which there's not some amount of overlap between the genuine in-distribution FRs and these hybrid sources. You get things right up to the end of the spectrum because what entropy measures isn't anomalousness, it's uncertainty, and there are some in-distribution sources which are even the correctly labeled ones, which is just very uncertain about.
Okay, that makes sense. It'd be great, I think, to quantify that notion as a baseline.
yeah, that's something which I think hopefully if I can get this behaving itself a bit more, that's definitely something that's going to be part of the write-up.
Okay, maybe you should move on. So thanks again, Fiona Porter.